cloud. As you know, we put the recording on the web page, just the link to the Dropbox folder with the file for those who wants to see your recording afterwards, if it's okay with you, of course.
Yeah, absolutely.
Okay, so I'm going to welcome those who joined today for this talk of the technical talks of CTSoc series. I'm Fabrizio Lamberti. I'm the Vice President Technical Activities of CTSoc. Together with the technical committees, we launched this series. And today, as you know, these talks are organized by two technical committees. Tonight, we have Dr. Christopher Kuhn from Munich, and he is representing the technical committee on automotive consumer electronic applications, and Mr. Ranish Pai from Synopsys, Sonmargan, India, and he is representing the technical committee on application-specific consumer electronics for Mars series. So before moving on and leaving the floor to them, and also to Yogesh Marathe to introduce the speakers, I would like, first of all, to give you, as usual, a quick introduction of the this idea, the technical talks, and the technical committee. So I'm sharing the screen and going full screen with this short presentation. So this is one of the events of this technical talk series, which has been created by IEEE Consumer Technology Association, Technology Society, and in particular by the technical activities area. So the technical activity area is one of the areas of CTSoc, which is combines with other areas like conferences, publications, industry and standards activities, education, etc. And basically, within the technical activities areas, we do have the technical committees and the future directions committees. You can find more information on the main website of CTSoc under the tab Technical Activities. We do have currently 15 technical committees, which have been established over the last 3 years and are covering the broad areas of interest of consumer technology society. So we have, as I said, application-specific consumer electronics for smart cities, audio-video system, automotive CE application, consumer communication network and connectivity, and so on and so forth. And these committees are part of the technical activities area, which include, as I said, the Future Directions Committee. And the technical committees are governed by the Technical Committees Board. And each technical committee has its own chair, vice chair, and secretaries. Together with CTSoc President, Professor Wen-Chung Kao, with VP Conferences, Professor Nobuo Funabiki, VP Publication, Professor Fabrice Labo, and the VP Industry and Standard Activities, Mr. Rahad Abdullah, and myself, we are, let's say, covering these technical activities areas. Each technical committee has its own mission, has its own websites, has its own members. And in particular, this is the list of officers which are currently engaged in the technical committees for the term 2023-2024. And by the way, in a few months, we'll have elections for the new term. Why is important to be a member of the technical committees? Well, first of all, how one can become a member of the technical committees. So basically, there's a technical activities membership application form on CTSoc website. This is the link, and you can apply. The application are screened by the officers of the technical committees, and if selected, the applicant can join the technical committees, at least one of the technical committees. And so far, we have more than 150, precisely more than 1,000 TC members. And now you don't have yet to be an IEEE member to be a technical committee member. You can be a member of the technical committees, and you can know about what is going on in the areas of conferences, publications, standard educations, and history. And so this is the goal. These are the goals and the objectives of the goal and the objectives of the technical committees. But the technical committees have also specific goals for each of the areas of CTSoc. So, for instance, regarding conferences, the technical committees review and approve the call for papers of conferences. They develop the call for papers. They provide publicity. They collect nominations for members to serve in the technical positions of conferences. They provide conference track and session chairs. They collect proposals for hosting conferences as well as for academic and industry speakers. So basically, they by joining a technical committee, you open yourself to a number of opportunities to volunteer in CTSoc and to be rewarded. So for instance, we selected technical position in ICC Las Vegas, ICC Berlin, Gaming, Entertainment and Media Conference, just closed this week. Associate editor positions for transaction in consumer electronics and consumer electronic magazines, special sessions in journals and magazines. You need to have one member of the technical committees on board to propose a special session in our publications and journals and magazines, organize workshops and special sessions. We are open to collaborations with other initiatives. So, for instance, one of the initiatives that has just been launched is the digital reality technical community. This is an initiative led by CTSoc, which is involving and is financially sponsored also by the Reliability Society, Electronic Packaging Society, Engineering and Medicine and Biology Society, Council on Radio Frequency Identification, Standard Association, Robotics and Automation Societies, and more. So, of course, if you want to get involved in these activities, please let me know. Here you have the link to the digital reality, but you can go on the website of CTSoc and you will find all this information. So regarding the technical talks, and then I will leave the floor to our great speakers, this is the already the ninth webinar of this series. The next talk will be in July. And as I said, today we'll have Christopher from Cyril Incorporated, Munich, Germany, and Rainish from Synopsys, Mountain View, California, and SmartGuide, India. And so I really thank you for attending today. I really thank our speakers for being with us today. And I leave the floor to Yogesh for introducing our first speaker. Thank you.
Sure. Thank you, Fabrizio. So, welcome everyone in the ninth webinar on Tech Talk. So, we are from CEA and SMC technical community, and we have two great Tech Talks aligned today. Let me introduce Dr. Christopher B. Kuhn. He studied electrical and computer engineering at Technical University Munich. He received his BSc degree in Electrical and Computer Engineering in 2016 and MSc in 2018. From 2018 to 2022, he worked as a PhD candidate at the Automated and Autonomous Driving Division of BMW Group, and also chair of Media Technology at TU Munich. In 2022, he completed his PhD with summa cum laude. So this is the highest honor for PhD. Honors, and his dissertation titled Failure Prediction for Autonomous Systems. This received Best Dissertation Award by IEEE Intelligent Transport System Society in 2023. His research interests are in areas of artificial intelligence, autonomous systems, and computer vision. And his current work is focused on explainable and compliant generative AI. His talk is titled Failures of Autonomous Systems and How to Predict Them. So this is Chris, and we also have Rajneesh Bajpai. He's a senior software professional and social entrepreneur based out of California, USA. He is best known as founder of SmartGaon, a non-profit organization operating in India. We would like to mention it is especially praised by Prime Minister of India, Narendra Modi, in his nationwide public addressal program, Man Ki Baat. He's working towards the integrated development of rural areas through latest technology and innovation. Rajneesh is certified agile professional and has extensive experience in delivering technology products and services in high growth environment. He has strong experience in building and managing cross-functional teams across the globe. He's also an advisor of various IEEE international technical conferences and startups on latest technology and innovation. So his talk is about rural transformation through technology innovation, the SmartGaon app and its impact. So I welcome both the speakers. Thank you for taking your time out to spread your knowledge. And I would first request Dr. Christopher B. Kuhn to start his tech talk, which is Failures of Autonomous Systems and How to Predict Them. Thank you.
Right. Yeah. Thank you for the very nice introduction and happy to be here. Right. And I'll share my slides. Okay. I hope everyone can see them.
Yeah.
Okay. Yeah. So, yeah, as you nicely introduced, I'm Christopher Kuhn. I'll present basically the most interesting insights and ideas from a research project I did together with Technical University of Munich and the BMW Group, which basically was all about the failures of autonomous systems and how you can predict them. So when you talk about autonomous systems, it's always important to think about what can they achieve. And one important thing to keep in mind is they inevitably fail in one way or another. So even most modern systems, even very finely tuned systems, they always make some form of mistake. And there are various ways of handling that, right, to avoid really dangerous situations on the roads. If you think about these 5 levels of automation that are typically talked about in autonomous driving, right, ranging from manual or assisted driving to full automation, where human has to do nothing at all, it's largely considered that level 3 is where we're mostly currently at. So it's conditional automation, meaning humans can kind of relax, but at some point it's expected that human operators have to take control again, either inside the car or perhaps via teleoperation. So someone else could remote control the car. So if something goes wrong, you can say, okay, that's fine. A human can take over and resolve the challenging situation. That raises the question, when should that happen, right? When should a human take over? And that's what this research project was all about. How can we detect situations where a human has to take control again automatically? The idea being the human should not have to pay attention all the time. So this has to happen automatically, so algorithmically. And since a human requires some time to prepare for taking control again, we also want to predict such failures as early as possible. So there's also a temporal predictive component. We want to buy as much time as possible to react to a potentially dangerous situation. So how can you do that? How can you predict failures of an autonomous system? For that, we looked at an autonomous vehicle in the most general form possible, basically. So you have some sensors that perceive the environment. That can be any number of LiDAR or camera or radar sensors. That sensor input is perceived in a perception module, right? That is then used to plan a physical trajectory, and physical control is exerted and the vehicle state changes. So that's as high level as it gets, but it's useful for then thinking about where do things go wrong and where can we detect it. That's also important. So first, let's treat the vehicle itself as a black box and just talk about system level failure. So that's what we did first. We looked at just the input and output of the system and the state, arguing we don't necessarily need to know what's going on inside under the hood, basically, to detect that something is going wrong. We can look at the input, where we looked at image-based failure prediction. You can look at the output, the trajectory, and predict failures based on that. And you can observe the state and argue that something is going wrong simply by observing how the speed or angle changes. Now that's very general and very black box, which has the benefit that you can do it even if you don't know exactly the details of the algorithms inside, but you of course want to know that. So you do want to look at the component level failures, which is what we did next, and predict if something goes wrong inside this driving stack. Here we focused on the perception module, which is where a lot of AI is also used these days or can be used. Specifically, we used semantic segmentation as a example of a perception task where things can go wrong and where you can predict it. And lastly, once you have predicted some failures, we also looked into applications of that. So how can you use this knowledge to perhaps mitigate and correct mistakes before even having to ask the human for help? And we did this at several points. So you can do this by monitoring the input from the beginning, and by later on, once the input has been perceived and used for something, you can try and correct mistakes that you've detected. So that's kind of the high-level way we approach this. So you can see we try to really look at the entire pipeline, really identify where can what go wrong, and more importantly, how can we measure and detect it. And yeah, I'm basically going to show some ideas of these three components next. So on the system level, again, we're basically treating the car as a black box. And here we're using an idea which is very fundamental to all our contributions here, which is introspective failure prediction. It's a pretty fundamental idea that you can observe failures of a system and learn from them introspectively. The idea is as this: any autonomous system has to perform some kind of test drives or has test data. Especially in driving, you have a lot of that. But you have Teslas driving on the roads. In Munich, you have BMW cars driving in their autonomous mode, and they drive and they have failures. Typically, a safety driver prevents crashes, not always, but mostly. But still, you get these situations where it would have led to a crash, basically. And we record that, or BMW records that, any company records that. So there's a lot of training data basically hidden in there. You can record the data such as the sensor input, the trajectories driven by the car, and you know for every recording whether it ended in failure or whether it didn't, whether it was successful. And that allows us to use machine learning to basically train a neural network to learn what patterns in the data indicate a failure. If we do this, if we learn to identify what patterns in all this data we observe in training and driving leads to a dangerous situation or doesn't, then during inference, right, during test time, we can simply observe the current data, right, the current sensor input, the current driven trajectory, use our model and see, is anything happening that in the past has led to an issue? And if you've observed enough problematic situations, then the idea is we can again assess a problematic situation arising simply by observing these patterns. So if you go into the details of how that can be done, without getting too technical, the idea is first we looked at the most simple representation of the system, which is its physical state. So basically speed, angle, acceleration, and angular velocity. Then we can observe how this feature vector basically of the state, how that changes over time. Here we looked at 3-second windows. So basically we argued that in the 10 seconds before a failure, that's where these patterns develop. So we split those 10-second sequences up into chunks of 3 seconds. That's what turned out to be best as a kind of compromise between not wanting to wait too long to detect something, but also having enough information to actually observe a failure pattern develop. And then we used these chunks basically of 3 seconds of state data that kind of track how the state changes as input for a temporal neural network. So we used LSTMs here, long short-term memory, basically a model that can extract temporal patterns from the input data. And a pretty simple model, honestly. We then basically trained it to assess whether this sequence led to a failure or not. That was the first approach we did. Of course, state data is very low dimensional, not super rich in information. So next we looked at a much richer source, which is images. Here you have a lot of information about what's going on. You have traffic signs, you have other traffic participants, you have the weather, a lot of sources where like in the physical world, failures can happen. Again, we looked at sequences of 3 seconds. Now, instead of taking all images, which would be a lot of images, depending on the rate, basically, we looked at different images. So we just want to see what changes over time. And those changes actually incorporate a lot of the information about what's then critical. So if you look at these images, you can see a car coming in from the right. And this actually caused a disengagement, like basically the human had to take control again due to the car cutting in from the right. And that is captured in the difference image. So you can see how the car appearing basically from the right is captured. And you can see how in the dynamic difference image, we're also capturing how this kind of develops. So we're capturing the entire development of 3 seconds in just a single image, which is really helpful for making the data more compact and normalize it so that when we deal with months of training sequences, we can handle large amounts of data here. And then again, we can train a model. Here we used a resonant variant to assess whether such a driving sequence leads to a failure or not, based on what we've observed in this test drive. And lastly, the last idea we looked at here is to look at the output of the system, not just the input, but the output. And that's an interesting source, because when you think about the trajectories that cars want to drive, they can show disagreement of the system with itself. So if you look at this toy example on the left, imagine there's like a problem ahead. The trajectories might disagree with each other. So initially the car wants to go right, then wants to go left, it wants to go right again. All the time the car is still driving straight ahead. So in this example on the left, you can see it's basically driving ahead for 3 seconds, even though it keeps switching its opinion, or the algorithm keeps outputting different ideas of where to go. And this disagreement with itself turns out to be pretty indicative of failures. On the right, we have some actual examples, where on the bottom you can see the trajectories driven by BMW test vehicles, where the trajectories diverge a lot when a failure is advancing, whereas in success sequences, the car largely drives exactly what it has intended to drive. Then you can put all of this together. So that's the idea of this framework we proposed. You have dedicated models for each source of failure. So you have those images, or you could also add any other sensor inputs such as LiDARs, radar. Then we have the low dimensional state vector, which is much faster to evaluate, but of course not as rich information. And you have the output where we use the trajectories. Of course, you could train a model jointly here, but we actually like this approach of doing a model in a modular fashion, because then you can really optimize each component separately and then combine them. In the simplest case, simply averaging the probabilities. Of course, any more complex technique here can also be explored, but we found that even just a simple average here already can combine the strength of each of those 3 sources of information. So let's look at some examples here when we evaluated this on months of BMW driving data. And we found that pretty much as expected, the least rich source of information, state-based, gave us less than 80% accuracy, which is already pretty nice. So we could correctly identify 80% of failure sequences just looking at this development of the state data in just 4 milliseconds. So it's very fast. Image-based is better at 85%, but also much slower since images need to be processed. But most importantly, combining all 3 ideas, state, trajectory, image-based, always improve performance, leading to almost 90%, still at less than 100 milliseconds per inference, meaning you could still do this at 10 hertz roughly, which is in line with how often a lot of these systems operate. Also, interesting to see how early in advance we could detect such failures. And here you can see all our different methods, and all of them get better as we get closer to the disengagement. So basically, the sooner the disengagement or the failure is, then the higher the prediction performance. But you can see even 7 seconds in advance, which is the earliest we looked, because before that we argued it's too far ahead to meaningfully look for patterns. You can see that even then we have a performance of over 85%, both for failure and success cases. So also not that many false positives or false negatives. And yeah, this basically is just in a black box approach where we don't even look into the components and just try to assess if something is going wrong, having learned from previous examples where something has gone wrong for the system. Still, we do want to look at the components. We do want to have ways of assessing when a component, such as a perception module, is failing. And here we looked at semantic segmentation as a very important component of perception. Semantic segmentation basically assigns each pixel in an image a semantic class. For example, this pixel is a car, that's road, that's a tree, right? Very important for assessing where can the car drive, where are there objects such as cars or pedestrians that we do not want to hit. But again, misclassifications are inevitable. On the right, you can see an image from Cityscapes, a very popular data set for driving examples. And there's a person between two cars. And he's kind of obscured, but he's definitely there, right at the edge of the road. However, by a state-of-the-art segmentation network on the bottom, you can see in black are all the misclassifications, in white are the correct pixels. Most things are correctly classified, but that person is overlooked. And that is, of course, dangerous. We do not want to overlook a person standing between two cars. So yeah, what can we do? Here, we again turn to introspection as an idea. And we argued, if we can predict the semantic class of a pixel, how about we try to predict whether each pixel is a failure or a success? So basically another semantic segmentation, but our labels are now not car or road or tree, but they are success or failure. So this is the workflow we proposed. Basically, you have error maps. Here we highlight them in green for correct and red for false. You use that as your training labels, and then during test time, you can directly take the test image and for each pixel predict would the semantic segmentation model get it right or get it wrong. And this way we could identify regions where the model is making a mistake. This is great for the current frame, but what about the future? Again, we want to be predictive. And here we went one step further and want to predict in advance, because it's of course critical to know where things will be in the future. So again, we have time to react. Here we used these error maps to extrapolate into the future. So by taking 4 consecutive error maps, we can actually extrapolate where a failure region might be. Here, for example, if you look at this error map, there's a cyclist in front of the car that's misclassified. And this cyclist is moving. So if you know that he's been moving to the left, then maybe we don't want to overtake that uncertain region on the left if we know it's going to move there in the future. So it's an important source of information that we can also assess where will our uncertain areas, where will our failures be in the next seconds. Then we evaluated this on some data sets, public data sets for semantic segmentation. We compared it to a state-of-the-art method for uncertainty estimation from back then, which was very general, deep ensemble, whereas this tailor-made introspection approach we proposed, which is trained specifically for a given model. Basically, every approach we proposed outperformed this generic uncertainty estimation method with the spatiotemporal model, where we trained it with a sequence of images so that we would not just learn spatial, but also temporal information about the scene. Led to the highest performance of 76% in area under precision recall curve. And also importantly, even 5 frames in the future, we still got a performance of 64%. Whereas if we had simply copied our current prediction, right, saying nothing will change over the next 5 frames, then the performance degrades, of course, because things do change over time in driving. But extrapolating to the future gives us still almost 2/3 performance here, so that we have a pretty good understanding of where will our segmentation fail in the future. Now that concludes basically those system level failure and component level failure prediction methods we proposed. And lastly, I want to talk about one idea we had of how to apply this, because it would of course be nice if we used our failure prediction knowledge to mitigate these mistakes without having to give up and having to ask a human driver for help. And here we directly continue with this pixel-wise failure prediction. And we turned to psychology actually as inspiration. And basically we argued that in psychology it's pretty much established that humans use what's called a zoom lens model to understand complex scenes. That works by first assessing the scene at a low resolving power and then using cues of what has been misunderstood to focus in a second look. And humans, we do that very quickly. So if you imagine entering a room, you immediately know there's a window, there's a table, there's a chair. But then to understand smaller details, such as small objects lying on the table, we tend to immediately then perform second focused looks without moving, just focusing on individual things and piecing together a very precise understanding of the image. And that gives humans great perceptive power. And we argued we can apply this to computer vision. The first view corresponds to the global first segmentation we've just seen. But then we can use this first segmentation to inform a second step. We can assess what did we get wrong in the first step, and then focus just on those local failure regions and reclassify them with a dedicated object classifier, which cannot deal with global scenes, but which can understand local patches. This is a pipeline we propose. It's kind of long, but let me just go through it on a high level. So first we do pixel-wise failures, understanding where in the image are we even getting things wrong. Then we focus only on the region of interest, which is typically in the middle of the frame. Then we cluster the resulting failure pixels to understand which regions have the highest error density. Here, in this case, that's 5 patches. There you can see that each time there are different objects that have been misclassified. Then we reclassify them with an object classifier, which is very high performing. So classifying is much easier than semantic segmentation. Then we only look at the pixels that caused this classification. So we use the class activation map here, meaning which pixels caused our classifier to say this is a person, for example. And then we change just the failure pixels. So we don't want to change, of course, the correctly predicted pixels. Yeah, so that's kind of the idea. We first say in these regions we got it wrong. We classify it again and we update pixels. Let's look at some examples. Here in the first row, we can see on the left, there are 2 people. In the ground truth, you can see those as yellow. Then in the predicted map, you cannot see them as yellow because they were overlooked. So the classification model, segmentation model, got them wrong. This incorrectly predicted area was detected by our failure prediction. Then the local classifier did correctly say, wait a second, this patch here, that is actually 2 people. And you can see the yellow pixels added back in on the right in this update. It's not pixel-wise perfect, but the information is recovered. Second row, you can see the same for a bicycle. Very hard to see in the original image. You can see it in orange in the ground truth. It is, again, recovered and previously overlooked. In the last row, you can see, again, a bicycle, which is classified as a person, so kind of close. But then we updated to have at least the bottom part as orange, meaning the bottom part is correctly classified as a bicycle. So you can see it's really on a pixelized level sometimes that we get it right, but overall, the important thing is misclassified regions get recovered. Yeah, so that concludes just those ideas I wanted to talk about. You can see we try to really capture the whole pipeline and propose ideas where you can detect things going wrong from the sensor input all the way to the state changing and everything in between. And yeah, we really managed to predict failures 7 seconds advance at almost 90% accuracy. 5 frames ahead, we could detect segmentation errors. We were then able to apply this to recover overlooked objects. And the downsides, of course, we do require extensive records of failures. Sometimes that is available, but of course, in other domains, it's not. And for novel failures in the future, it would, of course, be interesting to add new ideas from out-of-distribution detection, novelty detection, to be more prepared for failures that we could not learn from, to then be able to further detect failures of autonomous systems. Right, that concludes my talk. So thank you very much for your attention.
Right, thanks, Chris. That was really excellent. It's really cutting edge, and I think do we have a quick question? Maybe a minute.
I have one, but I don't want to steal time to Rainish. Maybe if you just can tell us if you are experimenting with, data set in which there are intentional, changes in the environment that are meant to make the system fail. I mean, you know that there are works in which someone has tried to alter the vertical traffic sign and stuff like that in order to make the system fail. Have you experimented with this
yes.
kind of data set? Do you have data sets?
Yeah, actually in the simulator, so not in real life, but we have did have a project in the Carla simulator, which is a driving simulator, where we had an algorithm that actually tried to maximize or minimize rather the time it took to make a car fail. And that we used to generate synthetic failure data. So we basically change parameters such as weather and traffic and environment. And based on a given driving stack, we then use this algorithm, which was basically using some Monte Carlo tree search to very quickly find the the environment parameters to make a given car fail, both leading to examples for introspective framework, but of course also giving us data about how to adjust the driving stack so that it wouldn't fail in the future. So we did do that in simulation, but I think also interesting to try that in real life and really purposefully try to generate failures in real life. But we have done it in simulation.
It's very interesting. I think it's this research is really intriguing. Thank you for you.
Thank you very much. Thank you.
Yeah. Thank you, Chris. Thank you, Fabrizio. Yeah. Let's go to our second tech talk. So Rajneesh, welcome. Over to you.
Thank you. So thanks, Yogesh, and thanks, Fabrizio and Christopher, for nice talk. And let me share my screen. So yeah, so myself, Rajneesh Bajpai, I'm working at Synopsys Mountain, California, and as part of my social responsibility, we initiated one initiative called Smart Gaon, and the main objective of this to bring enhance our rural communities with the smart technology so they can be future ready and future fit. So today I will cover a brief introduction about that initiative and also the impact, how it is helpful for rural communities. So this is Smart Gaon is a like one non-profit organization which we established in India, and as part of that we developed one app called Smart Gaon. And our vision with this objective is to empower villages so that our farmers can take smart decisions and they can be creative, innovative, and our villages can become self-reliant. So if you see here, this is the model where we try to cover different areas so that overall villages can be smart in all the areas with respect to smart governance, smart infrastructure, or healthcare, education, and agriculture side. And as part of this initiative, we divided in two parts. And one is because in rural areas, biggest challenge is the digital literacy. So what we did is we established centers in villages so that we can empower our villages and educate people with the latest technology, and they can use smart apps for the various purposes in villages itself. And the Smart Gaon, which I will talk more on this. And this is the a common platform, we can say, where we are trying to bring various technologies and in various areas, education, healthcare, or government schemes, everything together so that our farmers or villagers don't need to download different apps all together. They can one place and they can see everything at one place. So here are some pictures I would like to share. So those centers we established at different parts of the country in India. And this is the app which we developed, and you can also play with that. It's already available at Google Play Store. And let me cover this app part. If you see here, so this app has various features, like if any villagers because our intention is whatever technology, everything we are developing, the best use is if you apply those technologies at communities. So so as part of this, if you see here, this app contains all the features like villages and news section, government scheme, events, grammar features, agriculture and healthcare, and there also they have a complaint and everything they can do. So for example, if there is if we install for one village, so all the information about that village, you can get what is the history of the village, overview, and all the local attraction, everything together, it will be there. And also what we are trying to do, because there are various challenges how we can connect our rural areas with the globally. So as part of this, we try to provide all kind of newses like globally and local news, so that they can aware what is going in across the world, and the government schemes. So as part of this, we categorize into different sections, and we added all together so that if government is having various schemes, how they can leverage those schemes in their life, so they can go through it, they can know, and they can put their interest so that village head can take action accordingly. And other thing, if you see here, like grammar feature. So here we are trying to create a marketplace for the villagers, so that whatever, if they are growing some grains or pulses or vegetables, and sometime if you are not aware what is the current price of the grain or vegetable, they can easily know what is the current price is going on, so that that is very helpful for them, so that they can get the right value of their grains or pulses, whatever they are growing. So, and apart from that, what we are doing as part of this app is like agriculture side also, all the various features we are like they can talk to some agriculture expert, and even what is the market price, whether all these features they can know, and they can plan accordingly. So this is there. And healthcare also, telehealthcare, we have linked with various healthcare provider, and with this they can directly connect with the doctors without going to hospitals. Like if for a small disease or anything, they can just talk to those healthcare provider at home itself. And education side, also we are doing a lot, like all the like various coding skills, and whatever like AI ML concepts, we are trying to educate people so that they can, we are developing a lot of if you see because if I'm here in Silicon Valley, and daily lot of new things are coming in, but our goal is how these new technologies can go to root level of our world. So we are trying to educate also our rural communities, so that farmers and villagers and their kids can aware about these technologies. And apart from that, we have like various campaign, job surveys. So this is consolidated things all together. It's available. And also, if you see here, you can with this in background, we are using like, for example, Gen AI. So here because currently we are developing GenAI engine so that they can easily put their complaint or suggestions or if there is any announcements also, no need to go outside, like you cannot miss, and you can easily see that what is going on in the village. So so this is the brief like a introduction about this app. And now I'm coming to impact part. And so if we actually, what we did is in India, at the northern side of India, we there is a village called Todakpur, and what we did as a prototype, we as a pilot project, we applied all these technologies, and we saw the very good result over there. Like because as I was mentioning, these government schemes. So with those, because people were aware, and those were very helpful for people over there. So like public announcement systems we established across the village, and CCTV cameras, and we can easily see from our SmartGaon app. So whatever the PDS, which is like public distributions, we do, and there previously it was very less, but now it is increased, like around 90% people are getting on time all those government subsidies, grains and everything. And also complaints and everything with this app, it was very helpful, because now if village head is not available there, then also he or she can see at any time, oh, this villager is having this problem, and they can rectify it. Because with this we have both the admin and regular access, so that from the admin backend side, they can easily see what are the complaints and suggestions are coming from the village people. And we also used some like technology at schools, so that to make it more interesting for the students. So this is one of the good achievement we definitely got, is initially a number of students at that school was coming around less than 20, but within 4 years this count, because of this technology intervention, it increased from 20 to 120. And with our centers at villages, digital literacy also increased from 30% to 85%. So here are the some impact which we saw in last couple of years. So and the best and some of the key transformation you can see over here, like how it got changed, and these centers people are leveraging those things, and with the app it is very helpful over there. So as I said earlier, on the education side, we established center over there, and what we are doing is like a lot of research is going on various universities, and they want to apply like those research, and they want to try it out at various areas. So we are trying to provide this common platform, so that our research, like PhD scholars, they should not bother about oh, how we can deploy this. They directly, if you are really, it is your research is directly impacting our society, you can directly come to this platform, and you can try it out. And thanks to, I can say, various universities, they came forward and they tried, and it was really very impactful. So because this app we developed, it's a very easily we can plug in different features, and also those centers are helpful in like connecting with villagers, and training people. So so is part of like a smart education. We one organization came forward, and in last 2 years, like we trained around 2,000 students with the coding skills. And these are the public address systems, CCTV cameras, and so those are very like useful even during COVID time. I can say like this village had 0 COVID cases for 2020. So because everybody was aware, all awareness, webinars and everything with the app, we are communicating over there. So people are taking action accordingly. And the healthcare wise, like previously it used to the case like people have to go to like 4 or 5 kilometers and to visit doctor, but now for small diseases they can directly connect with the telemedicine center, and they can leverage the facilities or next, like they can take advice from the expert doctors. So and in last because we started this initiative in 2018, and now in 5 to 6 years, so we are already now working at the 20 more villages, and with the like around 15,000 plus people are already using a smart app, and in various states of India we are already working. And the good part is it's very well recognized at IEEE IC conference in Vegas also. And some time back, this Tech for Good, we got this first prize for this initiative. And even based on this model, some village was developed where they documented one documentary movie, and which was very appreciated at various film festival. And so in India, we are already working at various states like Maharashtra, Uttar Pradesh, Madhya Pradesh, Chhattisgarh, and Rajasthan. So, and this app is available not only in like Hindi, that is there, and some other regional language like English, Marathi, and so that way we are helping people. So, thank you.
Thanks, Rajnish. So, just for the audience, so I am also from India, and just to give you an extent, I just googled the number of villages in India are around 640,000 plus, and this has potential to impact lives of billions of people, right? And really great work, Rajnish. Thank you for sharing. Any quick question round the table? Who is online?
Just want to comment that I think that this talk, it's really inspiring, because it really, I like it the last slide with the impact, because really we are creating and impacting our societies in different ways. So Christopher presented us something that is incredibly impacting from the point of view of future technology. Here we are seeing how things are really changing already people's lives. So I really enjoyed your presentation. Thank you, Renish.
Thank you for inviting over here, and nice to meet with all of you. And we'll definitely, like in future, we'll have more interaction, so that we
Yes,
are
I hope
together.
that also sharing this video will help creating even more impact. So thanks again.
Thank you, Fabrizio, for doing this.
Thanks to all of
Thank
you for attending. So I would like to thank also Joges for moderating this talk today, and I want to thank you once again also for okay, we also have respected the timing, so it has been a pleasure meeting you, and hope you will join our next technical talks in July. And once again, thank you. Bye bye.
Bye bye.
Thank you.
All right.
Bye,
Bye,
everyone.
Thank you,
everyone.
everyone. Bye.